Okay, welcome. Today we are going to cover an introduction into hybrid fiber coax systems and how they work, what makes them up, and how does the signal get from anywhere to the customer. Now note that this will be covering a traditional hybrid fiber coax design, a traditional CMTS design, and will not cover remote PHY. Remote PHY will be covered under a different video. So the first question that comes to mind when talking about HFC or hybrid fiber coax is, what does HFC stand for? Hybrid fiber coax. It's exactly what it sounds like. It's a hybrid of fiber and coaxial networks. Now, each type of network has its benefits, and by using this hybrid model, we kind of take advantage of both of those systems, so we get kind of the best of both worlds. Coax is awesome because it is relatively cheap to implement. It is copper or copper cores, and it uses electrical pulses in order to send and receive data. Fiber is relatively expensive. It has a glass core, and it uses pulses of light to transmit data. Now, nothing moves faster than the speed of light, therefore fiber is the fastest. Of course, at the speeds we're talking about, it's completely negligible because our minds could not possibly process that difference or even come close to it. So, there's that. But one of the awesome things that is really cool about fiber is because of the light. Light is very clean, whereas electrical wires are susceptible to noise. And what noise is just interference on the line. So, we're using RF or radio frequency, which is also used for a lot of things like radio communications. Turning on and off your fluorescent light bulbs can actually interfere. Washers, dryers, other electrical equipment, even solar flares can interfere with the RF or the radio frequency signals in the wires. And because of that, over time, as this electrical signal goes these vast distances, the signal degrades from outside noise factor and just natural degradation of that electrical signal over the medium, over the copper medium. And eventually, your signal level will just start to kind of dip. It goes down, 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 down. Now we can actually amplify it and boost our signal level up again. And after a while it'll start to come down, 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 and we can amplify it again. However, there's actually limits to how many times we can do this, because when we're amplifying the signal, we're actually amplifying the noise as well. So any interference that we've gotten, any degradation of that signal, also gets amplified, as well as the data that we care about. So there is actually a hard limit to how many times you can amplify that signal before that signal becomes completely and utterly useless. Now on fiber, when we're talking about in the means of this course, it will be referenced in two different ways. We'll have what I'm going to call analog fiber and digital fiber. Now, the analog fiber is typically used in like a Prisma type solution, which we will cover a bit later, and the digital is used in an IP solution. So more to come on that, but it's important to note when we're using an analog system, it cannot be amplified and regenerated. When we're using digital, because of its IP nature, we can actually retransmit, regenerate. It's technically not a regeneration, but we can extend that indefinitely with our IP network. So if we have an IP network that covers hundreds and hundreds, if not thousands of kilometers, that's fine. We can do that. We have to put hops along the way of routers, controlling that IP network that fiber would run between, and we could have huge distances. I believe the max that you can get today is about 100 kilometers between devices, and each router would just basically create a new connection between them. So our data, which is now digital, can be retransmitted over and over and over again across these hops, and there's no limit, theoretically, to how many times we can actually do this. So distance is a huge thing, right? So plus distance, whereas coax has a hard limit to how far it can go. But it is cheaper. Now that being said, we take advantage of both of these because we use fiber in order to do the long distance transportations, and we use the coax in order to actually deliver the last mile, so within a system and then into each customer's home as well. So that being said, let's go ahead and clear this out, and we'll start again. So knowing that, we're going to start with what is very important for pretty much every head end. So at this point, we're in the head end. So head end. And in these head ends, we have a router usually. Now the router is the brains, and it has connections up to the core network, which is the very heart and soul of the ISP. So that's going to contain things like our connections to other service providers, our connections basically that make up the internet. Because the internet, or the World Wide Web, it's called that for a reason, because it is simply a web of service providers connecting to each other. That's all it is. So we have, oftentimes more than one internet connection as a service provider that comes off of our core network, along with other core services, which we do not need to get into for the scope of this. But the important part is in our head end, we have a router that has one or more connections going up to that core network. And the router will connect down to a device called a CMTS. Now the CMTS, or Cable Modem Termination System, does exactly what it sounds. It terminates all the cable modems physically and logically. We'll get into that a little bit more here. But basically, the CMTS in the head end will actually have physical connections to a combiner, which I'm just representing here as a C. And it sends all of the signals for all the cable modems into this combiner. And it will oftentimes have input signals from digital TV. Right, so this combiner is just taking all these different signals, which are just different frequencies, right? So let's go ahead and notate that. So this is just different frequencies. That's how it tells what something is, right? Your cable modems will communicate on certain frequencies. Your TV channels are on different frequencies. When you change between channels, you're actually just simply changing the frequency that you're tuning your device into. And that's it. So, excuse me. Out of that combiner, in this instance, we'll say it goes into a Prisma device, which we mentioned briefly before. And all this Prisma device is going to do is it takes coax and converts it to fiber. And we tend to send that fiber out to the outside plant. And the outside plant is something we're going to break down a little bit more. But the takeaway is it takes coax, or that RF signal, well, they're technically both RF in this instance, the radio frequency, but it takes coaxial copper signals out of the CMTS, right? So this is all coax from here on out. And it takes that coax and it turns it into fiber. That way we can transmit it longer distances to get it to where it needs to go. Now out in the field, it's going to hit something called a node. And this node does the exact opposite. It's going to take that, sorry about that, it's going to take that fiber and it's going to output coax. Now, of course, this is just an example, but in the field, in the copper plant, we're going to have the need to amplify the signal as we go. So there will be amps in line, line extenders, etc. We don't need to go into the differences of those. But eventually you're going to run into what's called a tap. And what the tap does is it allows you to tap into the hardline trunk cable here and bring it to your house. Right, so we have a little house here, awesome, and we go into that tap. Now we might have a string of taps, there may be many of them, connecting to many different homes, and each tap is capable of connecting to many homes as well. Now there's different value taps, and when they design these systems, they take into the consideration how many homes they think they're going to need to connect into, because each time you use this tap, you get a little outside interference, you get more signal degradation, etc. But that goes into your homes. And it's also important to note that this is just an example. These taps can be present before amps, after amps, anywhere in the coax copper network, not in the fiber network though. But let's break that down a little bit more. So when that tap, when it actually comes into your home, it's coming into, or it's actually coming to your home in something that we call a drop. And that's simply just a smaller cable that's not trunk hardline that we are able to bring signal into your home. And there it's usually going to hit a splitter because we can deliver multiple services, right? So off of that splitter in your home, you're usually going to have like a set-top box for your television, and you're going to have a modem for your internet. Now off of this modem, we can actually provide phone services as well. So there might be a phone connected to that modem, and off of that modem, the customer might have a router plugged in, a Wi-Fi router. Or we might give them a modem that is a modem router combo, right? So it doesn't matter if that's actually technically its own step or not, but the important part is either via wirelessly or plugged in with a cable, that router is going to get to a computer, a phone, a smart television, some device that's going to be consuming that internet. So the purpose here, the splitter is of course just splitting the signal, whereas the combiner is combining the signal. So the splitter's the exact same thing as the combiner, just in reverse. And from there we go to a set-top box. So the purpose of the set-top box is to decrypt digital video signals that we have sent, right? We have to have them encrypted because, well, a lot of our contracts require it. But we have to have it encrypted so people can't steal that signal. So when we authorize a set-top for certain channels, it can then decrypt those channels and then deliver them to the TV in an unencrypted format that the TV can understand. And then of course, you can view those channels. Now with the modem does something really cool as well. Its main purpose is to take coax in and deliver Ethernet and IP network, right? So this IP network is what's really underlying and running through this entire network. Even though it's going through different mediums, it is coming up IP all the way to the router, and IP all the way to the core network, and of course the internet itself is IP. IP stands for, you'll never guess, Internet Protocol. So of course it is the internet, it's what makes up the internet. But the modem simply takes that coax connection, converts it to Ethernet, and then of course it authorizes, right? The set-top box and the modem are both responsible for authorization. So it tells you, yes, you can get online, yes, this is the speed that you're allowed to get, and it also enforces that, and cool, you can have IP access. And it also does the same thing to the phone, right? It's just simply taking and allowing IP access for that phone, because we use VoIP or VoIP, which is simply voice over IP. Very simple. Now let's say, as a user here, right? And I'm actually going to undo that, and we're gonna grab a different color here just to keep this a little less confusing. But let's say we're the user here on our computer. Now we have this entire infrastructure in order to get this signal. But how does it actually work? When I go to my web browser and I type in google.com, how do I get there now? Right? So I type that into my PC. My PC is going to send that to a router, most likely. Whether that's a modem router combo, whether it's a Wi-Fi router here, but that router is going to be doing something that's called NAT, or Network Address Translation, right? So let's just write that down really quick. Network Address Translation. And all that does is sounds very complicated, but a very, very, very brief description of what it does is it allows this different types of IP addresses, right? There's public IPs that can talk on the internet. So any public IP can talk with any other public IP as long as we as the owner of that IP allow that to happen. And then there's private IPs. Private IPs cannot get past the boundary of the internet. They're not routable on the internet. They are just local to your network. And a network is defined in this scenario by every router creates its own network. And what that does is every time that you go on the internet, your computer will get an IP from your router. And it's going to get what's called a private IP. So that IP means nothing past this red line. It only means something within your home, within its own network, within your home network. And all NAT does is it takes the public IP that we get from the ISP, from the core network, and from the modem, from the core network through the modem. And it takes all these private IPs, because we might have 3 computers, we might have 10 computers, right? Each one gets a private IP. And it basically translates that communication to use the public IP. So you can have multiple devices sharing one single public IP. Because there's actually an IP shortage today. We're out of public IPs when we're talking about IPv4, which is, the main protocol of the internet. There's also IPv6, but we won't get into that today. And because of that, ISPs like us have had to come up with different solutions as to, we have a fixed number of IPs that we can use, but we have a need that outweighs how many IPs we have. And this NAT solution is the ingenious industry way to deal with that. So we let customers use as many private IPs as they want. They can match that to one single public IP that we give them. So if they have 5 computers, they don't need 5 public IPs. They just need one. And their router can do NAT, or Network Address Translation, to make sure that each individual user device has a private IP that can be translated and share one single public IP. So that hopefully wasn't too confusing, but from there, the signal just kind of goes up into the plant, comes up the drop into the tap, hops on this hardline trunk. It's coax, and it hits the node, gets turned into fiber, right? But the signal's still there. Now it's just analog, and from there, this is, of course, the extension of the plant, so technically it just kind of goes like this. But then from the Prisma, we'll take that fiber and convert it to coax. It's still RF, it's still analog. So an analog, just is a wave function like this. The high is a 1, the low is a 0. Pretty easy. But then what happens when we come to the CMTS is, of course, we're taking this coax medium and getting rid of it. That doesn't exist past the CMTS going up. But we take this analog and we convert it to digital. Right? So digital, there's no in-between values. It's either on or it's off. It's a 1 or a 0. So this is kind of how a digital signal looks like if you were to actually plug in and run that. Whereas analog, you have your low value and your high value, but you also have a bunch of different values in between. Digital, it's very clean. There's no ambiguity there, right? It's on, it's off. It's 1, 0. That's it. No 0.9, no 0.1, just 1 or 0. So as we come through here, based on what frequency we're communicating on, so once again the frequency thing, we know where to go, and we know that we're going to hit the CMTS. Now the CMTS, it of course converts, say, coax to IP, and analog to digital. That's its main purpose when we're going upstream, right? And of course downstream is just the exact opposite. But from the CMTS is where we're IP. We're using the internet protocol, we're completely digital, and we're hitting the router. Now the router is sort of like the brains of the operation. It says, hey guys, I know the way. I know the way to wherever you're trying to get. It's the gateway. It has the roadmap of where to go. It says you're trying to get to google.com. I know how to get there. And you need to take this path up to the core network. And the core network similarly has many routers in it. And each of those routers also knows the way, right? So each one of those knows how to get to wherever you may go in, whether that's Google, whether that's Amazon, somewhere else, right? Watching Netflix. So it traverses the core network, following all the roadmaps, and eventually out into the public internet. Now, the public internet is just a web of connections between all these different service providers. So it's going to hit other service providers' networks and many routers that also know the way. And it's eventually going to end up at the server for google.com. And it gets there. And then, of course, when it comes back, it says, I want to get to, I want to get back to this public address. And then it just takes the reverse route. Each router knows the way back as well, right? They have the knowledge for how to get out, but also how to come in. And each router on the internet also knows if I want to get to this public IP within our network, I know how to get there as well, and it will send it back properly, right? So it'll traverse this way all the way back down, and your search results show up. Same thing with voice. It's just an IP connection, except instead of going out to the internet, it goes to servers within our core network. So it never actually makes this hop. But it's the same exact concept. It just follows all the way up to the CMTS, where it gets converted into IP, and the router says, hey, I know the way, let me show you. This is where you need to go, and sends it on its merry way to our VoIP servers. And then your call is completed. The traffic comes back, and you now have two-way audio. And this all happens in the fraction of a time that it takes you to blink your eyes. This happens millions and millions of times. Anyway, this has been the quick introduction to a hybrid fiber coax plant, how it works, and exactly how the systems are laid out. Keep in mind this is a simplified version. However, we may do an advanced course one day. Feedback is welcome. Please submit, and we'll do what we can to make the next ones better. Thank you.